So yeah, we'll start now. This is a problem solving session for the NPTEL course Fluidization Engineering. So this is, I think it's week 4. So good afternoon everyone. So this is problem solving session for the NPTEL course Fluidization Engineering. So the course code is this one, and the courses have a problem solving session every Saturday between 3 p.m. and 5 p.m. And the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. And these sessions are handled by myself, Ankara Kartika. I am a research scholar from Department of Chemical Engineering, IIT Hyderabad. So we have seen the course starting and how we were proceeding. So it is like we'll be solving the problems related to that week's assignment, and the similar problems will be solved in this session. So it will be helpful when you are submitting the assignments. So if you have any doubts in that, you can ask me. So yeah, we'll start now. So course layout, we have seen that it is a 12-week course, and in the first few weeks it was about the introduction to the fluidization and flow pattern, gas distribution, bubbling fluidized beds, and we'll be dealing with entrainment, attrition, and these phenomena, everything that is happening inside the system. And we'll also be studying the mass transfer and the gas heat transfer phenomena happening inside the fluidized beds. So we all know that we have seen till now the introduction to the fluidization and the characteristics of solids, like how solids are classified into A, B, C, and D, and depending on the particle size and density, how the fluidization behavior is influenced inside the bed. So, and what are the regimes of fluidization? Everything we have seen till now. In fourth week, it is about flow pattern transition, and mainly associated with frictional pressure drop and modeling that. Later on, we'll be dealing with all the coming up things, and the problems will be solved based on that. And so, yes. Mm, just a minute. I think my system got hanged. Just a minute. Okay, if in between, if you face, if I face any internet connection, please wait in the meeting. I'll be joining in few minutes, like I'll use data and join. So if there are any fluctuations in the internet from my end, please wait a few minutes. That is my request. So coming back to the books and references, we have Kunia and Levenspil's Fluidization Engineering. This book, actually you can find it, and it will be very helpful if you read the book, because all the concepts will be covered from, related to fluidization is covered in this book, and it will give all details on fluidization, whatever findings have been there till that time. So everything is counted over here. Next is Gidas post multiphase flow and fluidization, continuum and kinetic theory description. So again, this is one book where apart from the fluidization aspects and fluidization phenomena, it will also be dealing with modeling of the fluidized beds. So we all know in fluidized beds we have two phases. One is solid phase and the other one is liquid phase. Fluid phase. Fluid phase might be liquid or air depending on the type of fluidization. So we all know we can model the fluid phase by using the continuum approach, whereas when we are dealing with solids, we can either go with the continuum approach or a Lagrangian approach, wherein we need to model individual particles. So if we are going with continuum approach, we need to know certain uh, properties of the solids, which will help us modeling the solids as continuum. So all those details are given in this book. Again, it is an interesting read if you can read. And third one is Gibbs fluidization dynamics, and last one is SK Majumder hydrodynamics and transport processes of inverse bubbly flow. And these are the books. Okay, now let us start with assignment problems. So this are just few sample problems for this week's related to this week's assignment submission. So we'll start in question 1. It is being asked that which one of the following does not influence the pressure drop inside the bed at particular fluidized condition. So which one of the following does not influence the pressure drop inside the bed at particular fluidization condition? And option 1, it is head. Option B, it is friction. Option C, it is acceleration of the solids. Option D, it is velocity. So particulate fluidization, what we mean by particulate fluidization is that after fluidization, if we are considering a liquid phase or a very low velocity of the gas, if we are passing low velocity of gas or if we are passing liquids, we will be finding fluidization such that there will be no formation, there will not be any formation of bubbles. Bubbles will not be formed inside the bed, and the bed will be uniformly fluidized by using the fluid. Mostly it will be liquid, or in some cases it can be low velocity gas as well. So particulate fluidization, it is like kind of uniform thing, and which does not influence the particle pressure drop inside the bed. So pressure drop inside the particulate fluidization does not depends on the velocity here, because after that how much ever we increase the velocity after particulate, I'm talking about the particulate fluidization condition, not in everything. So how much ever we increase or decrease the fluid velocity, there will not be any change. This is true at particulate fluidization condition. So the answer to this question is option D, velocity is the right answer. So we can see that answer is velocity. And now we'll go to question 2. Okay, yeah. When the gas solid two-phase flow in the riser reaches a fully developed state, the value of acceleration pressure drop should be. So here the question is, when the gas solid two-phase flow in the riser reaches a fully developed state. So the fluidization inside the bed has reached a fully developed state. So what would be the pressure drop due to the acceleration? So we all know that since it has reached the fully developed state, the acceleration, the value of acceleration pressure drop should be 0. Option A, it is 0. Option B, it is 1. Option C, it is 1.5. Option D, it is 2. So we all know that since it has reached the fully developed state, value of acceleration pressure drop would be 0 at this condition. Answer is 0. And now we'll go to question 3. Frictional pressure drop is caused by which among the following? So we are just saying frictional pressure drop, everything. So what exactly is frictional pressure drop? It is nothing but the pressure drop that is relating because of the movement of the fluid and the solid, and also like wall also comes into effect over here because the fluid and the particles are rubbing against each other. What is fluidization over here? By now we all know the meaning of fluidization. Fluidization is nothing but like we pass the fluid inside the packed bed, and because after at low velocity the particles would not be moving, and so the fluid would be passing through the voids in between, and the pressure drop would keep on increasing. So after that it would be like once it has reached the minimum fluidization condition, the velocity I am talking about, once we reach the minimum fluidization velocity, after which how much ever we increase the velocity, the pressure drop would remain the same, because after the minimum fluidization velocity the particles are starting to move, and because of that, like the particles are behaving like a fluid, so we call it as fluidized beds. So here the pressure drops comes into picture. Why? Because it is accounting the movement of particles, fluid, and also like wall effects would also be coming into picture. So we'll see the options first. The frictional pressure drop is caused by which among the following? Option A, Okay. First one, it is frictional force between the solid and the walls of the bed. Second one, it is frictional force between the gas and the solid. And third one, it is frictional force between the gas and the walls of the riser. So here we are given three statements. The first one is between solids and the walls of the bed. And this is true because in fluidized bed, the particles are also moving, and they would be moving against each other and against the walls as well. So the first statement is true because frictional force between the solid and the walls of the bed is coming into picture over here. Second statement is that frictional force between the gas and the solid. So again, like we are passing the gas, and because of the velocity increase in the velocity of the gas, the particles are also moving. So the gas and the solids are in continuous contact, and there is a pressure of because of that frictional force acting, arising out of that as well. And at last, frictional force between the gas and the wall of the riser. So again, this statement is true because gas is rubbing against the walls as well. So all three statements are belongs to the answer. So we'll see the options now. Option A, it is 1, 2 and 3. Option B, it is only 3. Option C, it is 1 and 3. Option D, it is 2 and 1. So answer is option A. 1, 2 and 3 is the right answer. Yeah. Answer is option A. 1, 2 and 3 is the right answer. So now we'll go to question 4. In question 4, it is given that fluid friction factor is calculated using the empirical Blasius formula for Reynolds number greater than 2300. So what it is given, fluid friction factor is calculated using the empirical Blasius formula for Reynolds number greater than 2300. So in this question, it is asking the formula for calculating the friction factor, fluid friction factor, when Reynolds number is greater than 2300, and we are using Blasius formula. So we'll look at the options first. It is option A, FF is equal to, that is friction factor is equal to 24 by REF, that is fluid Reynolds number. And second one is FF friction factor is equal to 0.079 divided by REF in power 0.25. And third one is uh, friction factor is 24 by REF 0.5 to the power of 0.5. And option D, it is 0.079 divided by REF power 0.75. So answer is option B actually. Yeah, answer is option B. It is FF is equal to 0.079 divided by REF to the power of 0.25. So in this question, what we need to focus is that we are asked to calculate friction factor. It is okay. And again, we are asked to use the empirical Blasius formula, and we'll be confident in that. So here it is two, the questions can come in two forms. One is when Reynolds number is greater than 2300, and if Reynolds number is less than 2300. So if it is greater than 2300, the formula is this, that is 0.079 divided by REF power 0.25. Whereas if it is less than 2300, I think it is 24 by REF is the right answer. Uh, you just check that once if it comes in any questions. So that is one thing. And yeah, the question can be asked in any form, like greater than 2300 or less than 2300, and you should be very cautious of that. So now we'll go to question 5. I think question 5 is a problem. We'll see. Okay. Consider that the particle is circulating with its terminal velocity in the bed. A bubbling fluidized bed of height 1.2 meter and diameter 0.04 meter is operated by air at an air superficial velocity of 0.15 meter per second, with sand particles of effective diameter 112 micrometer. Given that the air density is 1.2 kg per meter cube and density of the sand particles is 2600 kg per meter cube, wide edge of the bed is 0.55. Sphericity of particles is 0.85. Viscosity of the gas is 1.8 into 10 power minus 5 kg per meter second. Calculate the terminal velocity of the particles in meter per second. So first let us consider the question. In question what is being asked, you are asked to consider particle is circulating with its terminal velocity in the bed. So particle is circulating with the terminal velocity, and bubbling fluidized bed is there with bed dimensions given. That is, bed is cylindrical bed whose height is 1.2 meter and diameter is 0.04 meter. And what is the fluid medium over here? We are using air as a fluid medium, and air superficial velocity is 0.15 meter per second. And what is the packing? The packing is sand particles of effective diameter 112 micrometer. And so air has the density as 1.2 kg per meter cube, and density of sand is 2600 kg per meter cube. And wide edge is nothing but inside the bed, and again this void fraction is 0.55. So that is 45%. The 1 minus 0.55 is the packing fraction of the solids. So 45% of the bed is packed with the solids, and remaining 55% is filled with voids, that is they are empty. And the specificity of these sand particles is 0.85. And so we know the particles of the solid as sand particles, and we know its density and sphericity. And for we know the fluid medium as air, and we know its one density and viscosity, and we know the bed properties. So these are the main thing you need to be knowing when we are dealing with any fluid fluidization problem. That is, you need to know about the solids properties and fluid properties and the bed dimensions or whatever it is given over there. So in this question we are given everything, and we are now asked to calculate the terminal velocity of the particles in meter per second. So let us look at the options now. Option A, it is 0.656. Option B, it is 0.916. Option C, it is 0.987. Option D, it is 0.1691. So these are the options. So yeah, we'll just do the we'll calculate it by using the formula, everything. So we'll just see the answer first. Answer is 0.987. So from this we'll calculate it and get the answer. So for that, answer is over here. And first we need to identify what are all the given things. So as I have mentioned earlier, we need to we know three things from the problem statement. The first one is we know the bed dimensions. So bed dimensions, that is height and diameter of the bed is given. That is, height of the bed is 1.2 meter and diameter of the bed is 0.04 meter. And its void edge is, we know it as 0.58. And again, regarding the fluid medium, we know the it is air, and superficial velocity is given as 0.15 meter per second, and its density is given as 1.2 kg per meter cube. And viscosity of the air, again we know. So I would in general I would suggest you people to have some density and viscosity of air and the water memorized, so you can solve any problem directly. Like mostly these values would be around this range only. It would be 1.8 or 1.9 something. And the last one is we know the particles properties. Again, for particles we know its effective diameter, that is 112 micrometer, and we know the density and we know its sphericity. So now what are we asked to find? We are asked to find its terminal velocity. And how are we going to find? We need to know the formula, right? So for formula we have terminal velocity is equal to g into dp square into rho p minus rho f by 18 mu. In this, ut is the terminal velocity and g is the acceleration due to gravity, which is 9.81 meter per second, and dp is nothing but effective diameter over here, and rho p minus rho f, that is the relative density between the particles in the fluid. So particle density is 2600 and air density, that is fluid density, is 1.2 kg per meter cube, and divided by 18 mu. Mu is nothing but the viscosity of the fluid. So here we are doing the calculation, and ut is equal to 9.81, that is g into dp square, 112 into 10 power minus 6 the whole square, into 2600 minus 1.2 rho p minus rho f, divided by 18 into mu. Mu is nothing but 1.8 into 10 power minus 5, which is nothing but 0.987 meter per second. So from this, we are able to find the answer as 0.987, which is the option C. So once again, if we look at the question, what is being asked and what is given, we are asked to calculate the, the particle is circulating with its terminal velocity, and the bed dimensions is given as 1.2 meter and diameter 0.04 meter, and air is the fluid medium, and its superficial gas velocity is given, and particle properties are also given in terms of its diameter and density, and air density is given, and particle sphericity is given, voidage of the bed is given, and viscosity of the gas is given. So we are asked to calculate the terminal velocity. So first we have written the given things. So we know the bed properties and the fluid properties and the particle properties, and we are asked to find the terminal velocity. And from terminal velocity, for that we need to know the formula. The formula is nothing but ut is equal to g into dp square into rho p minus rho f divided by 18 mu. And on substituting everything, we are able to find the answer as 0.987 meter per second, which is the option C. So just take a look at it, and before we move on to next problem. So it would be like, if you have any doubts, you can ask. Just take a look at it for half a minute, and then we move on to next problem. So yeah, I hope it is clear actually, because we have the bed properties, fluid properties, and the particle or the solid properties, and we are asked to find the terminal velocity. So we have the formula as ut is equal to g into dp square into rho p minus rho f divided by 18 mu, and yeah, ut we have substituted. So we'll move on to next problem. Yeah, question 6 it is. In question 6 it is given the, the problem is that calculate the fanning friction factor of particles by using fanning equation for gas solid fluidized bed of diameter 0.08 meter, where frictional force per unit volume between solid phase and wall is 5.422 Newton per meter cube, and voidage of bed is 0.55. Particle density and velocity are 2600 kg per meter cube and 0.3 meter per second respectively. So in this question, we are asked to calculate for the fanning friction factor of the particles by using fanning equation, and the system under our consideration is gas solid fluidized beds whose diameter is 0.08 meter, and the frictional force per unit volume between solid phase and wall. Here we are given the frictional force per unit volume between the solid phase and the wall, which is 5.422 Newton per meter cube. So from this we are asked to calculate for the fanning friction factor of the particles. And again the bed voidage is given as 0.55, and particles density and velocity are given 2600 kg per meter cube, and velocity is 0.3 meter per second. So we'll look at the options. Options are option A, it is 2.072 into 10 power minus 3. Option B, it is 2.096 into 10 power minus 3. And option C, it is 2.059 into 10 power minus 3. And option D, it is 2.051 into 10 power minus 3. So everything is in very low value, and we'll look at the options, and again we'll go back and solve the problem. So answer is 2.059 into 10 power minus 3. So we'll solve the problem now. Yep. So first one, we know what is given. So we know the bed diameter is given, which is 0.08 meter, and frictional force per unit volume between solid phase and the wall is 5.422 Newton per meter cube. So frictional force between solid phase and the wall. So it is 5.422, and void age of the bed is 0.55, and particle density and particle velocity is given. So these are the given things from the question. And what are we asked to find? We are asked to find the fanning friction factor of the particles using the fanning equation, and we need to write the formula. So dp by dz particle wall is equal to 2 into fp into 1 minus epsilon divided by rho p into up square by d bed. So in this is the frictional force per unit volume, and 2 into fp, fp is the fanning friction factor for particles, and 1 minus epsilon. Epsilon is the void fraction or voidage, which is 0.55, and rho p is the density of the particles, 2600 kg per meter cube, and up is the particle phase velocity, which is 0.3 meter per second, and d bed is the diameter of the bed, which is 0.08 meter. So now we need to do the calculation. Here we have put 5.422, that is dou P by dou Z particle wall. The frictional force between the solid phase and the wall phase is 5.422 Newton per meter cube. So it is 5.422 is equal to 2 into Fp into 1 minus 0.55 into 2600 into 0.3 square. UP here is 0.3 meter per second. So UP square divided by d bed. D bed is the diameter of the bed, which is 0.08. So we substitute everything and we are able to find the fanning friction factor value as 2.0596 into 10 power minus 3. So if we go back and see the answer, it is 2.059 into 10 power minus 3. So in this, what is the key things to be noted here is that we are asked to find the fanning friction factor for the particles. So this thing is important. Like we are calculating it for particles, and what is being given, frictional force per unit volume between the solid phase and the wall phase. So these two things we need to be very careful while identifying the formula, and rest other things remains the same. That is, we know the gas solid fluidized bed and its diameter is straightforward, and void age of the bed is epsilon, that is 0.55, and particle density and particle velocity is given. So these two things we must be very conscious while we are solving the problem, that is fanning friction factor of the particles, and we are given the frictional force per unit volume between the solid phase and the wall phase, so which is 5.422. So these are the given things, and we are asked finding the fanning friction factor using this particular formula, where dp by dz, that is the pressure drop or the frictional force per unit volume between the solid phase and the wall phase, that is particles in the wall, is equal to 2 into fp into 1 minus epsilon rho p up square by d bed, and we know this value is 5.422 Newton per meter cube, is equal to 2 into fp. Fp here is unknown, and 1 minus epsilon. Epsilon is 0.55 into rho p. Rho p is nothing but particle density, that is 2600 kg per meter cube, and up is 0.3 meter per second. D bed again is 0.08. We substituted everything and taken everything to the other side, and we are getting the value of fp as 2.0596 into 10 power minus 3. So this is how we got the answer. So answer is this. So just take a look at it. We'll go to next problem. Like we'll see the next problem. So again, this is a straightforward problem. So I hope it is clear. We'll go to next one now. Okay. So it is question 7. In question 7, again it is a problem, and what are we asked? We are asked to consider that the particle is circulating with its terminal velocity in the bed. A bubbling fluidized bed of height 1.2 meter and diameter 0.04 meter is operated by air at an air superficial velocity of 0.09 meter per second, with sand particles and of effective diameter 105 micrometer. Given that the air density is 1.2 kg per meter cube and density of sand particles is 2600 kg per meter cube, void age of the bed is 0.55, sphericity of particles is 0.85, calculate frictional pressure drop between gas and the wall. Friction factor of gas is 0.166. Okay, here thickness, it is circulating with terminal velocity and bubbling fluidized bed and whose height is 1.2 meter and diameter is 0.04 meter. And we are using the air as the fluid medium and its superficial velocity is 0.09 meter per second, and the sand particles have an effective diameter of 105 micrometer and air density is 1.2 kg per meter cube and density of sand particles is 2600 kg per meter cube. Voidage is given and sphericity is given. Friction factor of gas is given. So we are asked to find the frictional pressure drop between the gas and the wall. The before the problem before the last problem, we calculated the frictional pressure drop between the solid particles. Solid and the wall. Sorry, we were given the frictional pressure drop between the solid and the wall, and we were asked to calculate the frictional factor of the particles. So in this question, it is just another thing where we are given the frictional pressure drop between gas and the wall, and we are asked to calculate the friction factor of the gas. Sorry, we are given the friction factor of gas and we are asked to calculate the frictional pressure drop between the gas and the wall. So it is just a reverse way of, not reverse way, it is another part to the question. So we'll solve that, and before that we'll just look at the options. Option A, it is 0.1259. Option B, it is 0.1466. Option C, it is 0.1280. Option D, it is 0.1499. So answer is actually option B, that is 0.1466 is the option. Is the answer. So now we need to see how to solve this problem. For that we'll check the answer. Okay, question 7. So first we'll just mention what is being given in the question so that it will be clear for us to identify things when we are solving the problem. So first one is that given things, bed properties are given. Bed height, its diameter and the voidage. So bed height here is 1.2 meter and diameter of the bed is 0.04 meter and voidage is 0.55. Is that given in the 0.04 and 0.55. And fluid is we know the fluid is air and its density is 1.2 kg per meter cube and its viscosity is 1.8 into 10 power minus 5 kg per meter second. So these are at the standard conditions. The density and the viscosity of air at standard conditions is these values, and unless until given you can take these, like if values are given you can take those, otherwise you can take these at the normal conditions. And the superficial air velocity is given as 0.09 meter per second, and particles, its effective diameter is given 105 micrometer and density is given 2600 kg per meter cube and sphericity is given 0.85. So with density, diameter and sphericity, you are able to imagine the particle structure and the particle behavior. You can just say how the particles behave inside the fluidized beds. For example, with density and the fluid known, we can and the size known, we can say the geldat class under which that fluidized bed would be coming under. So we can say that these particles will be behaving in a so and so way inside the fluidized bed. So those things you can say from these properties. And last one given is friction factor of gas. So gas FF is given, that is 0.166. So now what are we asked to find? We are asked to find the frictional pressure drop between gas and the wall. And what are we given? We are given the we are given all these things, and now we need to know the formula. Formula is dp by dz fluid wall. Here it is given, we are asked to find the frictional pressure drop between the gas and the wall, that is fluid and the wall. So it is given by dp by dz at fluid wall is equal to 2 into ff into epsilon into rho f into usf by epsilon the whole square divided by d bed. So in the particle wall formula, it was almost the same, where we used dp by dz particle wall is equal to 2 into f t into 1 minus epsilon into rho p into u p by up square by d bed. Okay, it is question 6. I thought question 5. Okay, it is same problem. I mean, same particle wall. Instead of fluid wall, it was asked. In the formula we used was particle wall. It is equal to 2 into Fp into 1 minus epsilon into rho p up square by dB. Here we are again dealing with fluid and the wall. So it is 2Ff instead of 1 minus epsilon. 1 minus epsilon gives solid fraction inside the bed. So when we are dealing with particle wall, we are using 1 minus epsilon, whereas when we are dealing with fluid wall, we are using epsilon. And here it is particle wall, so it is particle density, and up is particle velocity divided by d bed. So whatever the things we use for particles, we are using it for fluid in the formula. So it is 2 into ff into epsilon rho f into USF divided by epsilon the whole square. Here we are not directly using the velocity because it is a superficial gas velocity, so we are dividing by the epsilon, that is the void fraction or the volume fraction of the fluid from volume fraction, air fraction, everything whatever it is, USF by epsilon the whole square divided by d bed. So the formula is the same, but components in the formula are differing. So now we are asked to find the dp by dz at fluid wall. So it is equal to 2 into ff epsilon rho f usf by epsilon the whole square divided by d bed. So again here we know that ff is the friction factor of gas, which is 0.166, and epsilon is the void fraction, so it is 0.55, and rho f is the density of gas, which is 1.2 kg per meter cube, and usf is superficial gas velocity, it is 0.09, and epsilon is again 0.55, and d bed is 0.04. So we are now calculating the dp by dz at between the fluid and the wall. So it is 2 into 0.166 into 0.55 into 1.2 into 0.09 divided by 0.55 the whole square divided by 0.04. So it is 0.1466. We are getting the value as 0.1466. So dp by dz between the fluid and the wall is 0.1466. So this is what is asked in the question. So if we go back and look at the question, we can read the questions once again. Consider that the particle is circulating with its terminal velocity in the bed. A wobbling fluidized bed of height 1.2 meter and diameter 0.04 meter is operated by air at an air superficial velocity of 0.09 meter per second with sand particles of effective diameter 105 micrometer. Given air density is 1.2 kg per meter cube and density of sand particles is 2600 kg per meter cube. Voidage of the bed is 0.55 and sphericity of particles is 0.85, and frictional pressure drop between gas and the wall is need to be calculated, while we are given the friction factor of gas, which is 0.166. So answer we got is 0.1466, so it is 0.1499 is given in the option. Okay, option B, it is 0.1466. It is D is 0.1499. So don't get confused. Answer is option B, that is 0.1466 is the right answer. So this is how we done. We have just used the formula to find the frictional pressure of between the fluid and the wall, between the gas and the wall. So it is given by 2 into ff into epsilon into rho f into usf divided by epsilon the whole square divided by d bed. D bed is diameter of the bed. So it is a direct substitution, similar to last problem where things asked were friction factor while given the pressure drop. So here we are asked to find the pressure drop given the friction factor. So this is how we are, we have done the problem. So just take a look at it. We'll go to the next question in some time. So just be clear. This problem and last problem are kind of similar, so it is just a direct substitution. So see this for 20 seconds and we'll go to the next problem. So yeah, I hope it is clear. Question 7 is clear. Now we'll go to question 8. Pressure drop in the gas liquid solid system is obtained by. So here now we are dealing with three-phase system, that is liquid, solid and the gas. So pressure drop in gas liquid solid system is obtained by pressure drop due to head, friction and the acceleration. Pressure drop due to head, vacuum and acceleration. And option C, it is pressure drop due to flow, head and friction. Option D, it is pressure drop due to acceleration, slip and friction. So here we are given the pressure drop in a three-phase system, that is gas, liquid and solid system. Why, what are all the factors causing the pressure drop inside the systems? So answer is actually option A, head, friction and acceleration. Because head is nothing but because of the fluid flow difference, it is causing some pressure drop, and the frictional pressure drop between the caused due to the movement of the solids and the fluids, and solids and the wall of the particles, and the fluid and the wall of the particles, and also again acceleration. So all these things contribute to the pressure drop in the gas liquid solid systems. So answer is option A, pressure drop due to head, friction and acceleration is the right answer. So answer to question 8 is option A. Now we'll go to question 9. In question 9, it is asked that according to Venn and Yu 1966, drag coefficient for fluid solid and the drag coefficient for a single particle are interrelated as. So what is asked here, in according to Venn and Yu's formula, that is 1966 approach, drag coefficient for the fluid solid and the drag coefficient for a single particle are related as. And here it is CDFP is the drag coefficient for fluid solid particle, and CDP is the drag coefficient for single particle. So and epsilon GL is the volume fraction of the gas liquid mixture, and USG is the superficial velocity of gas. And option A, it is CDFP by CDP, that is here it is given as the ratio of the drag coefficient for the fluid solid particle, and fluid solid, and divided by the ratio of the drag coefficient for a single particle, and it is given by epsilon GL in to the power of 8 USG minus 5.2. And option B, it is again CDFP divided by CDP is equal to epsilon GL to the power of 8 USG minus 5.4. And option C, it is CDFP divided by CDP is equal to epsilon GL to the power of 8 USG minus 5.7. Option D, it is CDFP divided by CDP is equal to epsilon GL to the power of 8 USG minus 5.0. So answer is, I think, option C, CDFP divided by CDP, that is drag coefficient for solid particles. Fluid solid to the drag coefficient for the single particle is given as epsilon GL to the power of 8 USG minus 5.7. So here it is like we are having the system of fluid and the solid mixture, and drag coefficient for a single particle. When we allowed the single particle settling, we have a single particle drag coefficient CDP, or we in general we can call it CD naught. So it is related to CD naught into epsilon G and to the power of 8 USG minus 5.7. USG is nothing but superficial velocity of gas, and epsilon GL is the volume fraction for the gas liquid mixture. And that is option C is the right answer, which is given by Venn and Yu 1966. So now we go to question 10. In question 10, it is asked that in fanning equation, where dP by dZ is equal to particle wall pressure drop, frictional pressure drop. So here in fanning friction factor, fanning equation, we have seen like in previous slides itself while we were solving the problem. So dP by dZ is between the particles and the wall. It is denoting this particle wall frictional pressure drop, and UP is denoting particle velocity, and dp by dz particle wall is proportional to UP power 1.5, or dp by dz particle wall is proportional to 1 by UP cube, or option C, it is dp by dz particle wall is proportional to UP power 1 by 2. Option D, dp by dz particle wall is proportional to UP the whole square. Like we have seen the problem while while we were solving the problem, that dp by dz particle wall, like frictional pressure drop between particle wall is directly proportional to UP to the power of whole, I mean proportional to UP square actually. So it is option D is the right answer. Option, okay, I mean it is not option A. Option D is the right answer. Option D is the right answer, where dp by dz particle wall is directly proportional to UP square, and dp by dz we know the formula, which is dp by dz particle wall frictional pressure drop between particle and the wall is given by 2 into fp into 1 minus epsilon into rho p UP square divided by d bed, where d bed is the diameter of the bed, UP is the particle velocity, rho p is the density of the particles, and epsilon is the void fraction, and 1 minus epsilon is the solid volume fraction. Because in the system only solids and the fluid is present, so epsilon is void fraction, so epsilon plus solid fraction is equal to 1, solid fraction is equal to 1 minus epsilon, so this gives solids fraction, and Fp is the friction factor, fanning friction factor for particles, and dou P by dou Z is the frictional pressure drop between the particles and the walls. From particles in the wall, frictional pressure drop. So in the question, it is asked that in fanning equation, where dp by dz particle wall is equal to particle wall frictional pressure drop, and UP is the particle velocity. So if that is the case, what is dp by dz proportional to UP to the power of x? If that is the case, what is x? X is here 2, that is it is proportional to the square of the particle velocity. As we can clearly see from this formula, particle wall frictional pressure drop is directly proportional to the square of the particle velocity. So this is what is given. Now we'll go to question 11. In question 11, it is given that friction factor for fluid for Reynolds number less than 2300 is calculated by dash. Okay. Friction factor for fluid for Reynolds number is less than 2300. When Reynolds number is less than 2300, how will we calculate the friction factor? Fluid friction factor FFW, and it is given by dash. So where FW is the fluid friction factor and REGL is the Reynolds number of the gas liquid mixture. So we need to identify how we calculate. It is FFW is equal to 24 by REGL, and it is equal to option B, it is 0.079 divided by REGL power to the power of 0.25, and option C, it is FFW is equal to 24 by REG to power REGL to the power of 0.5, and option D, it is FFW is equal to 0.079 divided by REGL to the power of 0.75. So answer is, again here we need to be conscious because it is less than 2300. It is asked in less than 2300. So friction factor formula for fluid when Reynolds number is less than 2300. So it is 24 by REGL is the right answer, I think. Option A is the right answer. So FFW is equal to 24 by REGL. Similar question was asked in the first few problems, where it was asked when if Reynolds number is greater than 2300, we saw how it is 0.079 divided by Reynolds number to the power of 0.25. using Blasius formula. So here it is as less than 2300. There it was greater than 2300. Here it is less than 2300. One thing you can remember is that in low Reynolds number, mostly in the formula, that is drag coefficient, everything would be coming as 24 by RE, like here it is frictional factor for the fluid, which is 24 by REGL. Similarly, when we are dealing with the low particle Reynolds number, that is REP, here it is fluid Reynolds number, it is less than 2300. But if we are dealing with the particle Reynolds number less than 0.1 or something, so we call it as in the laminar regime. So if in that case, we calculate the drag coefficient, which would be coming as 24 by REP. So similar to that is given here, but here instead of particle Reynolds number, we are dealing with the fluid Reynolds number. And if it is less than 2300, how we are calculating the friction factor? So it is again 24 by REGL is the right answer. So option A is the right answer. And now we go to question 12. In question 12, it is given that in a three-phase fluidized bed, when the liquid velocity increases, delta PFR divided by L, what happens to that? In a three-phase fluidized bed, when the liquid velocity increases, then delta PFR by L, what happens to that? So, okay, delta PFR. So delta PFR here is nothing but frictional pressure drop, and L is the length of the bed. So delta PFR in a three-phase fluidized bed, when liquid velocity increases, what happens to frictional pressure drop per unit length of the bed is what is being asked. So in options, it is option A increases, option B decreases, option C remains constant, option D none. Actually, in two-phase fluidized bed, when liquid velocity increases, pressure drop remains a constant actually. But in three-phase fluidized bed, it does not remain same. Rather, it decreases because you will be having the influence of gas also in addition to the liquid. So here you are facing influence from gas phase, liquid phase, and the particle phase. So there will be hindering of the motion, and the pressure drop would be again decreasing when the liquid velocity is increased. So this happens in three-phase fluidized bed. So be careful, in three-phase fluidized bed, when liquid velocity increases, then frictional pressure drop per unit length of the bed decreases. So this is not the case with two-phase fluidized beds, as we all know. But in three-phase fluidized beds, liquid velocity increases, frictional pressure drop decreases. So this is with question 12. Now we'll go to question 13. In question 13, it is asked that bank of model for bubbly flow is developed based on. So option A, it is viscosity of phases. Option B, it is density of phases. Option C, it is interfacial shear stress. Option D, it is flow rate of the medium. So all these are theory questions actually. So Bank of model for bubbly flow is developed based on interfacial shear stress. Option C is the right answer. So Bank-of model for bubbly flow. So it is developed based on interfacial shear stress. Option C is the right answer. Now moving to question 14. Which flow pattern is used for predicting frictional pressure drop according to the Wallace model 1969? So according to Wallace model 1969, what is the flow pattern used for predicting the frictional pressure drop? So option A, it is slurry flow. Option B, it is annular flow. Option C, it is multiphase flow. Option D, it is vertical pipe flow. Option B is the right answer. So like which flow pattern we are annular flow pattern is used for predicting frictional pressure drop according to the model given by Wallace 1969. So answer is option B, annular flow is the right answer. In question 15, okay, yeah, property index IP is represented by dash. So here in the options, mu SI is the viscosity of slurry, and mu G is the viscosity of gas, and I think it is mu SL, mu to be mu SL. Yeah, mu SL is the viscosity of slurry. Property index is represented by option. Okay. In the options, mu SL is the viscosity of slurry, and mu G is the viscosity of gas, and rho G is the density of gas, and rho SL is the density of slurry. And so, what is the option for representing property index? So, option A, it is mu SL by mu G to the power of zero point 0.2 and divided by rho SL by rho G. Option B, it is rho SL by rho G divided by mu SL by mu G to the power of zero point 0.2. And option C, it is mu SL by mu G to the power of zero point 0.4 divided by rho SL by rho G. And option D, it is rho SL by rho G to the power of zero point 0.4 divided by mu SL by mu G. So here it is, property index actually is given by the ratio of viscosity of slurry to the viscosity of gas divided by density of slurry to the density of gas. So option A and option C only comes under that. So option B and D are false. So if we look at the power for the ratio of viscosity, we can see that it is zero point 0.2 in option A and 0.7, 0.4 in option C. So right answer is actually option A. I think it is 0.2. So yeah, property index is represented by ratio of viscosity of slurry to the viscosity of gas to the density of slurry to the density of gas. So that is what is given by property index formula. Uh, yeah, IP or property index. So now we'll go to question 16. Okay, actually the time now is 4 o'clock. So we'll take a small break and then we'll come back. We'll come back by 4 and then we can start by 4 5. And just a 4 minutes break. We'll join again. So I will start now. Question 16, it is about, it is asked that frictional pressure drop can be calculated using Locke and Martinelli correlations in single phase flow, three phase flow, and option C, it's two phase flow. Actually, our answer is two phase flow as well as three phase flow. And so our answer is option B and C. Both options B and C is the right answer. So frictional pressure drop can be calculated using Locke and Martinelli correlations in three phase flows and two phase flows. So option B and C, both options B and C are right. So answer to this question is option D. Yeah, option D is the right answer. And so question 17, it is about, in the fluidization process, the pressure drop is used to govern change of the fractional holdup of the phase, patterns of energy dissipation, assessment of fluidized bed performance, all the above. Answer is all the above. So why? Because why are we worried about pressure drop in the fluidization process? Because it is an important phenomenon. I mean, important thing that is governing so many things. Pressure drop is very important when we are dealing with the fluidization process. Why is it important? It is important because so many other factors depend on the fluidization. I mean, pressure drop. For example, if you are running some cases and you are observing some drastic pressure drop or drastic some things, you will be worried about why it is happening, and some things might be going wrong. So it is an indication of so many things, and whether things are going right or whether things are going wrong, or even how I mean under what state it is. Like if we will be passing the fluid inside the bed, and we'll be observing the pressure drop to identify at what condition and the bed is transforming from the packed bed condition to the fluidized bed condition. So in those things we should be knowing that, mm, I mean we'll be understanding the importance of pressure drop. So that is why we need to we need to know about the pressure drop. And in from the options given, it is like option A, it is change of the fractional holdup of the phase, and option B, it is patterns of energy dissipation, option C, it is assessment of fluidized bed performance. So yeah, it gives us an idea about assessment of the fluidized bed performance and patterns of energy dissipation. Of course, it's like we can identify what is going wrong or what is going on in the system. And option A, it is change of the fractional holdup of the phase. Again, these things we can identify because it would be like fluctuations in pressure drop we would be measuring, and it would be giving us idea into so many things. So all these things are the right answer. Option D is the right answer. So option D is the right answer. Option Now we'll go to question 18. In question 18, it is given that with increase of particle diameter, minimum fluidization velocity dash. So what happens when we increase the minimum fluidization velocity? So option A, it remains constant. Option B, it increases. Option C, it decreases. Option D, none of the above. I think it increases. Okay, with increase of particle diameter. Okay. Okay, with increase of particle diameter, minimum fluidization velocity increases. This one actually I'm not sure, but I think with increase of particle, just a minute, I'll just confirm this once. So yeah, actually with increase of particle diameter, minimum fluidization velocity increases actually. When we increase the particle diameter because of the packings everything, uh, the minimum fluidization velocity also increases because like what happens is that at higher pressure drop the particle, higher velocity, the particles would be easier to particles would be fluidizing, before which the particles would be remaining in the state of packed condition only. This is with when we are dealing with particle diameter. So the question might also come from other factors as well. So just check those things as well. So in this particular question, it is that with increase of particle diameter, minimum fluidization velocity, option A it remains constant, option B it increases, option C it decreases, option D none of the above. So answer is option B, increases is the right answer. And now we'll go to question 19. Okay, question 20. I just skipped, I think. Okay, which among the following equation can be used to define mixture fraction factor? FM. So, which among the following equations can be used to define mixture fraction factor? So, first one it is Bernoulli's equation. Second one Navier-Stokes equation. Or okay, mixture I think it is friction factor. Option C it is Fanning friction factor. Fanning friction equation. Option D it is Hagen's partial equation. So which among the following equation can be used to define mixture friction factor, not fraction factor? So it is like answer we all know it is Fanning's friction equation. So answer is option C. Mixture friction factor is calculated using Fanning friction equation. So answer is option C. Now we'll go to question 20. Okay. These problems that we have seen till now belongs to problem category where we are dealing with problems similar to question 4. Sorry, week 4. So the 19 questions that we have seen now will give you an idea how to solve the week 4 assignment and submit it. So the questions that we'll be seeing hereafter, some 20 questions are there, I think. So those are the answer to, discussion for the answer to the week 3 assignment problems. So from the week 3 assignments, we are just seeing that. So we'll see the questions. So multi-phase flow behaviors, these are all just assignment problem only, but belongs to week 3. So multi-phase flow behaviors are affected by interfacial tension forces. Option B, wetting characteristics of the liquid on the channel wall. Option C, contact angle and the exchange of mass, momentum and energy between the phases. Option D, all the above. Uh, all the above is the right answer because multi-phase flow behaviors are affected by interfacial tension forces. Yes, it affects because we have the fluid and the solid medium, and the interfacial tension forces is again important because we might be dealing with three-phase systems also, like where we'll be dealing with gas, liquid and the solid. So interfacial tension forces is important, and wetting characteristics of liquid on the channel wall and contact angle and exchange of mass, momentum and energy between the phases, all three factors are affecting the multi-phase flow behaviors. So answer is all the above. And now we are seeing question 2. Okay, multi-phase flows like two-phase flows, three-phase flows, then three-phase flows. Examples for two-phase flows, we can even consider oil and water system, and we can consider three-phase flows meaning like air, oil and water, air, ice and water. All these things are like we can see interfacial tension forces and wetting characteristics of liquid on the channel wall and contact angle. So everything is like playing a role. So that is question 1. In question 2, in case of homogeneous or particulate fluidization, as the gas velocity increases, bed expands smoothly in a homogeneous manner. Option B, further increase of gas velocities, bubbles are formed in the bed. Both option A and B, none of the above. Option C is the answer where both A and B is true. Because in case of homogeneous fluidization is the condition where we pass the velocity at low velocity, I mean, gas would be at low velocity. Generally, it is a term associated with liquid-solid fluidization. But if we are dealing with the gas-solid fluidization, it would be at a low velocity. And after that, the with increase in that low velocity, the bed would be expanding smoothly. There would not be any large voidage inside the bed. So as gas velocity is increased, bed expands smoothly in a homogeneous manner. That is what we call it as a homogeneous or particulate fluidization. Further increase of gas velocity beyond that regime, if we increase the gas velocity, bubbles will obviously be formed. So bubbles are formed in the bed. So in homogeneous or particulate fluidization, there is no formation of bubbles. So as the gas velocity increases, the bed expands smoothly in a homogeneous manner, but with further increase of gas velocity, bubbles are formed in the bed. So both are true. Therefore, in case of homogeneous fluidized beds, options A as well as B is true. So the right answer is option C. And if we go to question 3, okay, just an in idea of fluidization regime. So we call this as smooth fluidization. So we can see that with low velocity, there is particles are not moving inside the bed, whereas at minimum fluidization condition, the particles have in a loosely packed state. With increase in the fluid velocity, we can see that smooth fluidization. This is what we call as particulate fluidization. Also, it is mostly associated with a liquid regime, but if it is a gas, it would be at a low velocity compared to the bubbling regime. So there is no formation of bubbles in the smooth fluidization. But with increase in the velocity, with further increase in velocity, we will be able to see the formation of bubbles. So that is what is the fluidization regime. And now we see question 3. In question 3, it is given that in case of bubbling fluidization, the bubble size increases as gas velocity increases. Bubble size decreases as gas velocity increases. Bubble size remains unchanged as gas velocity increases. Option D, none of the above. Option A is the right answer. Bubble size increases as gas velocity increases, because we can see that in case of bubbling fluidization, let us consider these three as bubbling fluidization with increase in the fluid velocity. Like this is from increase of the towards the right, we are able to see fluidization regimes when fluid velocity is increased. So we can see that this is at a lower gas velocity compared to this. So this is at low velocity, this is at a higher velocity. So with increase in the gas velocity in the bubbling fluidization, the bubbles will grow in size and they will almost occupy the size of the column actually. So that is again we call it as a slugging, but in general with increase in the gas velocity, bubble size will increase. Bubble size increases as gas velocity increases is the right answer. Option A is the right answer to this question. Now we'll go to question 4. If most of the bed cross section is captured by bubble or void, phenomenon is called bubbling fluidization, homogeneous fluidization, slugging fluidization, all the above. It is slugging fluidization. Yeah, in the previous fluidization regime diagram itself, we saw that when bubble size almost reaching the size of the column, if most of the bed cross section is captured by bubble or void, that is if almost 60% of the column diameter is occupied by the bubble or void, we call it as a slugging fluidization regime. So first one is bubbling fluidization regime. With further increase in the velocity, the bubbles grow in size and almost reach the size of the column. That is what we call as slugging fluidization. So with if most of the bed cross section is captured by bubbles or voids, we call it as a slugging fluidization. If this cross section is occupied by bubbles, it would be bubbling fluidization. And if no bubbles are there, we call it homogeneous fluidization or smooth fluidization, particulate fluidization, everything. And now we go to question 5. In question 5, in which fluidization pattern clusters of particles move downward near the wall while gas containing dispersed particles moves upward in the interior? So gas is moving in the upward regime, in the upward manner in the center of the bed, and near the walls the cluster of particles are moving downward. That is happening in which regime? So let us look at the options. Options is option A, fast fluidization. Option B, it is pneumatic conveying. Option C, it is spouted fluidization. Option D, it is all the above. Should be option fast fluidization. Okay, in spouted fluidization, actually there will be formation of large bubbles, and in fast fluidization, it is like the gas will be moving in the interior and the particles will be moving near the wall downwards. So so okay, fast fluidization, we can say that like gas particles will be moving and the particles are moving downward near the walls. Like near the walls, the gas is moving, while in this, sorry, near the walls, the particles are moving downward. Whereas in the, I mean, this would be like before this, but still, like for your understanding, I'm just showing this, but it is a turbulent fluidization. So, and gas is moving in the center. So, the question is, in which fluidization cluster of particles move downward near the wall while gas containing dispersed particles move upward in the interior. So it is happening in the fast fluidization. So answer is option A. Fast fluidization is the right answer. Now we go to question 6. In question 6, in which fluidization pattern particles travel like a piston with relatively high pressure drop and a high feed rate of particles? I think it is spouted. Okay, option A, it is fast fluidization. Option B, pneumatic. Okay, pneumatic conveying. Option C, it is powdered fluidization. Option D, all the above. Okay, option B, pneumatic conveying is the right answer. Okay, okay. Here it is. Yeah, we are taking all the particles away from the bed. In which fluidization pattern particles travel like a piston with relatively high pressure drop and a high feed rate of particles. So here again, if we go back to the diagram, we are able to see that pneumatic transport, like feed rate of particles will be high and they will be like traveling outside the bed. So answer is pneumatic conveying. Yeah, answer is option B, pneumatic conveying fluidization. So now we go to question 7. In question 7, it is given that according to By and Grace 1995, maximum stable bubble diameter as at the slug condition should be less than. So according to By and Grace, maximum stable bubble size. So we have seen that the bubbles will grow in size and they will break and disperse the solids contained with them at the top of the bed, and this would be happening. So when does bubbles break and that things happen? It is so it happens when the bubble reaches almost size of the almost the size of the column diameter. So when does the bubble size remain stable? So it should be less than 66% of the column diameter. Option B, it is 56% of the column diameter. Option C, it is 46% of the column diameter. Option D, none of the above. So answer is actually 56% of the column diameter is the right answer. According to By and Grace, the maximum stable bubble diameter at this condition should be less than 66% of the column diameter. Option A is the right answer. Yes. Okay, now we'll go to question 8. In question 8, the rise velocity is controlled by the equipment and they become slugs of gas when size of the bubble is greater than about dash. So option A, it is one third of the column diameter of the equipment. Option B, it is two third of the diameter of the equipment. And option C, it is half of the diameter of the equipment. And option D, it is none of the above. Uh, uh, Option A, it is one third of the diameter of the column. So what is it, I mean, what is being asked is that rise velocity is controlled by the equipment, and bubble rise velocity is controlled by the equipment and they become slugs of gas when size of the bubble is greater than. So we call bubbles bubbling bed as bubbling fluidization when it is bubbles are less than size. Bubble sizes are small, and with further increase in velocity we are able to see it, the slugging regime, where after slugging regime these bubbles break in size and recirculation happens. That happens when bubble diameter is greater than 66 percentage. It happens. So bubbles, I mean 66% of the diameter of the column, but if it is less than 66% of the diameter of the column, we call it as we say that we have stable bubbles. But when do we say that they are slugging regime? It is that when the diameter of the column is one greater than one third. So you can remember that if it is greater than one third of the diameter of the column, it is known as slugging regime. Whereas if it is greater than two third, the bubbles are not stable. If it is greater than one third, they are slugs, and after two third, these bubbles are unstable. That is the right answer. So here the question is about when they become slugs of gas when the size of the bubble is greater than about one third of the diameter of the column. So option answer is option A, one third of the diameter of the equipment. So now we go to question 9. Question 9. Before achieving pneumatic transport, the transport operated fluidized bed at fixed solids flux GS also experience option A bubbly flow, option B slug flow, option B slug flow, option C turbulent flow, option D all the above. Actually, just give me a moment. I'll be coming now. I mean, just look at the options and see the answers. I'll just. Actually, just a small correction in previous question. Okay, I think we are good. Okay, yeah, we are good. We'll just continue. Okay, before achieving pneumatic transport, the transport operated fluidized bed also experience bubbly flow, slug flow, turbulent flow, all the above. So from the fluidization regime itself, we know that uh, like before the pneumatic transport happens at the highest velocity. I mean not highest, but at very large fluid velocity, the particles escape the bed. So that is what is happens in the pneumatic transport. So before pneumatic transport, what are all the things happens inside the fluidized bed as we increase the things, that is fluid velocity, the transport or operated fluidized beds also experience. So however, before we are not directly jumping into pneumatic transport, so we'll be going in a stepwise increase of the velocity. So we and the bed also experience bubbly flows. Yes, bubbly flows happens when the fluid velocity is higher than the minimum fluidization velocity, and if very much higher than the smooth fluidization. And also it happens when the bubbles are almost stable in size, that is we can call it bubble size would be less than one third of the diameter, I mean less than one third. So after one third of the diameter of the column, if bubble sizes are larger than one third of the diameter of the column, we call it as a slug flow. And after that, after two-third of the diameter of the column, the bubbles will be breaking in size and we see the turbulent flow. So all these things are seen in the transport operated fluidized beds before we achieve the pneumatic transport. Pneumatic transport is the last thing that we will be experiencing inside the fluidized bed. So our answer is all the above is the right answer. Option D is the right answer. So now we'll go to question 10. In question 10, it is given that in batch operated fluidized beds, option A, particles are not exiting from the bed. Option B, particles fed in are transported out of the bed. Option C, either A or B. Option D, none of the above. So in batch operated fluidized beds, actually the particles are not escaping the exiting from the bed. So that is why we go with the batch operated conditions and we are not allowing the particles to exit the bed. So answer is option A. Option A, that is particles are not exiting from the bed, is the right answer. So that is question 10. We'll see question 11. In question 11, the classical choking depends on bubble size, which is related to dash. So option A, relative motion between the gas and the solid space in case of continuous bed, and on superficial gas velocity in case of batch operated bed. Options A and B, both option A and B. Option D, none of the above. So answer is option C, both A and B is the right answer. Why? Because choking in fluidized bed occurs when the depends on the bubble size. So what does bubble size depends on? It depends on the superficial gas velocity when we are dealing with the fluidized beds. I mean batch operated fluidized beds. We need to know the superficial gas velocity. Or if it is a continuous bed, we need to know the relative velocity or the relative motion between the particles and the gas we need to know. So only then we can say that the bubble size would be depending on these factors and the choking is depending on these. So choking in vertical pneumatic system happens in three ways. So the first one is accumulative choking, and type B it is blower or standpipe induced, and type C it is classical choking. Classical choking is what is asked in this particular question. But in accumulative choking, solids start to accumulate at the bottom of the conveyor as the saturation gas capacity is reached. Type B is that choking is that, like we all know what choking is, right? That the particles would be like movement would be disrupted, and so it is accumulative choking where the solids are accumulated at the bottom of the conveyor. And type B is that blower or standpipe induced. Instability is due to gas blower conveyor or solids feeder conveyor. So if there is any instability because of that, again choking occurs. And type C is the classical choking where it is due to slugging regime transition to severe slugging, classical choking occurs. So here it depends on the bubble diameter, bubble size. So bubble size, so when classical choking, so therefore it, since it is associated with transition to the slugging, we say that it depends on the bubble size. And what does bubble size depends on? It depends on the fluid velocity, that is the fluid inlet velocity. So it is superficial gas velocity in case of the batch operated bed. If it is a continuous operated bed, it is between the relative motion of the solids and the gas particles. So both options A and B are right, which is given by option C. So that is question 11. In question 12, what type of choking occurs when diameter of pipe is small and comparable to that of a bubble involving geometric limitations beyond hydrodynamic factors? So what type of choking occurs when the diameter of the pipe is small and comparable to that of the bubble involving geometrical limitations besides hydrodynamic factors? So if the diameter of the pipe is small compared to that size of the bubble, what does it here mean? It means that bubble size here plays a huge role, and therefore what comes to our mind, we get the classical choking. So because in classical choking only it depends on the transition to the slugging regime, so bubble size plays a huge role in that case. So if diameter of the pipe is small and bubbles is small compared to that of a bubble, so bubbles is almost reaching the size of the column, so it means that classical choking will occur. So option A, accumulative choking, false. Option B, classical choking. Option C, blower or standpipe induced choking. Option D, all the above. So answer is option D, classical choking, because if we consider the size of the bubbles has reached the size of the column or size of the pipe, we say it is classical choking. Classical choking is there. So that is the answer to question 12. If we go to question 13, for pseudo-homogeneous flow regime, particle Reynolds number value is. So in flow regime, we can see that it is homogeneous flow regime, pseudo-homogeneous flow regime, and heterogeneous flow regime. So if it is a homogeneous flow regime, the Reynolds number is very low. That is, it is less than 10 power minus 6. Whereas if it is greater than zero point 0.1, we call it heterogeneous flow regime, and pseudo homogeneous flow regime is between 10 power minus 6 to 1. So if the Reynolds number is very low, that is less than 10 power minus 6, that is homogeneous flow regime, and if it is greater than 0.1, it is heterogeneous flow regime, and if it is between 10 power minus 6 to, okay, okay, 0.1 to 2, okay, if it is in between, yeah, okay, I just messed up with the value. If it is greater than zero point 0.1 and less than 2, it is pseudo homogeneous flow regime. If it is less than zero point 0.1, we call it homogeneous flow regime, and if it is greater than 2, we call it heterogeneous flow regime. So if it is this, it is pseudo homogeneous. If it is this, it is homogeneous. If it is this, it is heterogeneous. Now I think I'm clear. If it is less than 0.1 but greater than 10 power minus 6, it is homogeneous flow regime. If it is less than 2 but greater than 0.1, it is pseudo homogeneous flow regime, and if it is greater than 2, it is heterogeneous flow regime. So answer for pseudo homogeneous flow regime is 0.1 to 2 is the right answer. Option B is the right answer. Now we see question 14. An increasing liquid velocity beyond minimum fluidization velocity, the regime becomes dash. Increasing the liquid velocity beyond the minimum fluidization velocity, the fluidization regime becomes dash. Option A, it is conventional fluidization regime. Option B, it is circulating fluidization regime. Option C, it is hydraulic fluidization regime. Option D, it is none of the above. So answer is increasing the liquid velocity beyond the minimum fluidization velocity. The first thing to occur is conventional fluidization regime. So after that, with very high increase in the velocity, circulating regime, everything comes into picture. But the first one is that increasing the liquid velocity beyond the minimum fluidization velocity. Once we cross the minimum fluidization velocity, we experience conventional fluidization regime. So answer is option A. Option A is the right answer. So, if anyone was saying anything, you can say. Okay. Now it is question 15. In question 15, it is asked that a discrete bubble flow pattern predominates at dash. A discrete bubble flow pattern predominates at dash. So answer is option. We look at the options first. Option A, it is low gas and high liquid velocities, and option B, it is low gas and low liquid velocities, and option C, it is high gas and low liquid velocities. Option D, it is none of the above. Option B is the right answer. Here we are concerned about the discrete bubble pattern. So bubble size is discrete. Bubbles are discrete in identifiable. So that happens when it is low gas and low liquid velocities. We are able to find discrete bubble flow pattern when we are considering the gas and the liquid velocities inside the bed. So when the liquid velocity is low and the gas velocity is low, we are able to see the discrete bubble flow pattern. So that is question 15. Now we go to question 16. Dispersed bubble flow pattern characterized by the small bubbles. Option A, the dispersed bubble flow pattern characterized by the small bubbles. Option A, it is with less uniform size distribution than discrete bubble flow pattern. Option B, it is with more uniform size distribution than the discrete bubble flow pattern. Option C, it is with equivalent size distribution than the discrete bubble flow pattern. Option D, it is none of the above. So what is the distinction between the discrete bubble flow pattern and the dispersed bubble flow pattern? In the last question, we have seen that how discrete bubble flow pattern is predominated at low gas velocities and low liquid velocities. Low gas and low liquid velocities. So here we are seeing about the dispersed bubble flow pattern, and is characterized by the small bubbles. Dispersed bubble flow pattern characterizes by the small bubbles. Uh, when in comparison with the discrete bubble flow pattern, what is the size distribution? So they have more uniform size distribution actually. Even though the bubble sizes are small, their size distribution is more uniform than discrete bubble phases. Even in discrete bubble phases, it would be like uh, bubble sizes may not be small, but size distribution is less uniform than the dispersed phase. So in dispersed phase, as you can see, the name suggests that it is a dispersed medium, dispersion. So it is more uniform size distribution than the discrete bubble flow pattern. So option B is the right answer. Yes, option B is the right answer. Now we go to question 17. In question 17, it is given that for a homogeneous flow regime, the Reynolds number is given by. So this we have seen in the last question itself. It is answer is 10 power minus 6 to 0.1. So option A, it is 10 power minus 6 less than REP less than 0.1, and it is option B 0.1 to 2. Option C, it is greater than 2. Option D, none of the above. So similar to the last question, the option A is the right answer because it is given as homogeneous flow regime. Homogeneous flow regime, the particle Reynolds number is 10 power minus 6 to 0.1. Option A is the right answer. 0.1 to 2, it is pseudo homogeneous flow regime. Greater than 2, it is heterogeneous flow regime. It is for homogeneous flow regime, it is 10 power minus 6 to 0.1. Option A is the right answer. So now we go to question 18. In question 18, it is asked that in case of slug flows, as gas velocity is increased further, bubble becomes larger and more elongated. Option B, at low liquid velocity, onset of slug flow is almost independent of liquid velocity. Option C, at high liquid velocities, the transition from dispersed bubble flow to slug flow is a function of liquid velocity. Option D, all the above. So we'll look at the statements first. In case of slug flow, As the gas velocity is increased, bubble becomes larger and more elongated. So this is true. Like if we increase the gas velocity, the bubbles almost reach the size of the column that we have seen. So the bubbles are growing larger and they are also getting elongated. So first statement is true, and of second statement it is at low liquid velocity, onset of slug flow is almost independent of low liquid velocity. So again this is true. At low liquid velocity the slug flow is almost independent of the liquid velocity, that is onset of slug flow. And at higher liquid velocities, transition from bubble dispersed bubble flow to slug flow is a function of liquid velocity. So at low liquid velocity, onset of slug flow is independent of liquid velocity. At higher velocities, however, the transition from dispersed phase to slug flow is a function of liquid velocities. So all three statements are true, therefore answer is all the above. So we'll go to question 19. In question 19, the elongated, distorted Taylor bubbles are formed in the coilless bubble flow, slug flow. Option C, it is churn flow. Option D, it is all the above. So churn flow is the right answer. The elongated, distorted Taylor bubbles are formed in the churn flow. Yeah, answer is option C. Now we'll go to last question of today's. Okay, this is actually problem from last week. I have given a solution for last week, solution to a problem in last week. It is question 14. So this week is actually from week 2 assignment actually, I guess. So that I discussed in the last week. So there is one more approach to this particular problem which gives us a more equal answer. So the last week the answer that I have given was approximate answer. So but in this there is one more approach. So I am giving that approach which gives you the direct answer actually. So we'll see that problem. So this is the last problem for today's session. Calculate the terminal velocity for the sharp irregular sand particles. Calculate the terminal velocity for the sharp irregular sand particles whose density is 1.2 into 10 power minus 3 gram per centimeter cube and viscosity is 1.8 into 10 power minus 4 gram per centimeter second, and dp star is given by 160 micrometer and density of solid is 2.6 into gram per centimeter cube, 2.6 gram per centimeter cube, and phi s, that is sphericity, is 0.67. So we are asked to calculate the terminal velocity for sharp irregular sand particles, and for that we are given the density. I mean we are using terminal velocity in the gas medium, and the density of gas and viscosity of gas is given. Density of gas is 1.2 into 10 power minus 3 gram per centimeter cube or 1.2 kg per meter cube, and viscosity of gas is 1.8 into 10 power minus 4 gram per centimeter second, or again it is 1.8 into 10 power minus 5 kg per meter second, and dp star is 160 micrometer and density is 2.6 gram per centimeter cube or 2600 kg per meter cube, and sphericity phi s is 0.67. So answers is 88 centimeter per second, option B 66 centimeter per second, option C 77 centimeter per second, option D it is 55 centimeter per second. So answer is 88 centimeter per second. So last week there was one solution, so I am just giving a different solution. So answer is 88 centimeter per second. I mean different solution meaning different way of approaching the problem and getting the answer. So yeah, we'll see question 14. I mean the answer is, first we'll write the given. Given is density of gas is 1.2 kg per meter cube, viscosity is this, dp star is 160 micrometer and density of solid is this. And we are asked to find terminal velocity ut, and the formula is actually we are supposed to use three formula. The first one is we need to find dimensionless diameter and dimensionless terminal velocity, and from this dimensionless terminal velocity we are to find the actual terminal velocity. So first we need to find the terminal and dimensionless diameter. So for that dp star is equal to dp into rho g into rho s minus rho g into g by mu square to the power of 1 by 3. So dp star is given by 160 into 10 power minus 6, that is 160 micrometer, into g is 1.2 kg per meter cube, into 2600 kg per meter cube minus 1.2 kg per meter cube into 9.81 divided by mu square, that is 1.8 into 10 power minus 5 the whole square. I have just put separately, but it is the same. So is equal to the power of 1 by 3. So that gives us dimensionless diameter as 7.28. And from this dimensionless diameter, we are calculating the dimensionless terminal velocity. ut star is equal to 18 by dp star square plus 2.335 minus 1.7445s divided by dp star to the power of 0.5 and whole to the power of minus 1. So again we are substituting everything over here and getting ut star as this. One 1.2938 and it okay u star no, it is like u star not u is equal to this, u is equal to u star divided by this. Okay, so first we are calculating the dp star. Okay, and dp star we are getting a 7.28, and from dp star we are calculating the ut star, where dp star we are substituting in ut star formula and getting this particular value. And after getting ut star, we are substituting the values back in the formula and getting the u value. So u star is equal to u into this particular formula. Now we are getting the u, so we are just dividing that by that 1.2938. I'll just confirm this once because I didn't put division symbol, so I'm just little worried. Minus 5 into 9.81 into 1600 minus 1.2 power 1 divided by 3. Okay. Into 1. Okay. 18 divided by 7.28 plus just a minute, 1.744 into 0.67, 2.335 minus this divided by 7.25 5.5 plus 18 divided by 7.8 whole square. Star is equal to okay. It actually comes as into only 1 point. I don't know why. 4g square 1.2 square. Okay, I'll just confirm this again in the next class. If there are any other doubts in today's class, you can ask this question. I'll confirm again in the next class. Did you say anything now, actually? Okay. If there are any doubts, you can ask, or else we can see in the next class. This problem alone I'll keep again next class. Like, I don't know why I multiplied here. Okay, thank you. We'll see you next class. Thank you for attending.